The key issue here, once you get to the tetrahedral intermediate, is the leaving group, is the Y group a good leaving group relative to the negatively charged kicker offer? And we described various scenarios where that might be the case. For example, Cl minus is a good leaving group, so in this tetrahedral intermediate, you would expect lone pair electrons on the oxygen to kick down and kick off Cl minus, and that's going to give you this substitution product. And again, your comparison is the leaving group once it's left versus the negatively charged oxygen. Is this a good enough kicker offer? We've seen a situation where we expected this reaction to be very favorable in the forward direction if the leaving group is a methoxy group, as in this tetrahedral intermediate. We predict it to still be reasonable, but perhaps not as favorable in the forward direction. We might expect this step to be reversible. And finally, we had an example where, no, that's not a good leaving group at all relative to the negatively charged oxygen. And so there we would sort of be stuck. Okay, there is something else we need to talk about in addition to the fate of the leaving group, and that is this issue of nucleophilic attack. This is something that I probably should have talked about earlier, but when you have a carbonyl compound and you've got a nucleophile, the basic question that you want to ask is it reasonable for the nucleophile to attack the carbon-oxygen pi star? And the way we're going to make that assessment is really going to be very similar to the way we talked about, is the leaving group good enough to leave? That is, we're going to envision what happens when the nucleophile, if the nucleophile were to attack the pi star. We're going to draw the proposed tetrahedral intermediate, and then we're going to ask the question, how reactive is that nucleophile relative to the negatively charged intermediate that you get once the attacking happens? Okay, so again, we're going to be thinking about the reactivity of the nucleophile versus the negatively charged oxygen. And again, we can compare pKa's of conjugate acids to get an idea. For example, we might say, what about hydroxide? Could hydroxide attack this carbonyl to get a negatively charged oxygen in a tetrahedral intermediate? And we'd ask ourselves, basically, what is that equilibrium constant? We would compare the stability of the nucleophile when it's on its own, OH minus, versus the negatively charged intermediate in the tetrahedral intermediate, and we'd say, are they about the same stability? Is one more stable than the other? In this case, the conjugate acid of OH minus is water, which if you remember, has a pKa of 16, and that's pretty similar to the conjugate acid of our tetrahedral intermediate, which also has a pKa of 16. So based on reactivity of those two intermediates alone, we would say, yeah, this is totally reasonable, but it's probably reversible, meaning at this stage, a negatively charged oxygen could very easily kick off the OH minus, and we could go back to starting materials. Do you see how that's almost the same questions we were asking about the Y group anyway? Making a judgment as to what's happening. We're just doing that now with the nucleophile. So we're asking, can the nucleophile attack? Is the nucleophile likely to just get kicked right back off? And we're asking basically that same question about the leaving group. Let's give an example where probably a nucleophile isn't strong enough to attack directly. So what if our nucleophile were water? Okay, here's your carbonyl compound, and we're going to be asking, is this reasonable? Let's draw the intermediate. Let's go ahead and draw the arrows, because the arrows are the instructions for drawing an intermediate. So here's what the tetrahedral intermediate would look like. Oh shoot, let's see, we put the Y group there. There's the new bond with water that we just made. And we're basically asking reactivity of negatively charged oxygen versus in the tetrahedral intermediate versus the reactivity of the nucleophile. Conjugate acid of water is H3O+, which has a pKa of -2. Conjugate acid of your tetrahedral intermediate, again, is an alcohol with pKa 16. You would predict here that water is a much, much weaker nucleophile and much, much less reactive than the negatively charged oxygen in the tetrahedral intermediate. So you'd predict that actually water wouldn't be able to attack directly. You'd predict that this equilibrium constant would be way, way, way less than 1, and that this would be not reasonable. Okay? That makes sense? And think of it this way. A neutral water probably isn't reactive enough to generate a negatively charged oxygen in a tetrahedral intermediate. What if you're in that situation? Are there ways around it? Well, sure. If your nucleophile is not strong enough to attack on its own, that's when you need catalysis. So we're going to see later on in a future chapter acid catalysis of nucleophiles attacking carbonyl compounds. Let me give you an example of how this might happen. And this is just a preview. There's no examples of this in chapter 13. But what if we included some acid, the HOMO of a carbonyl compound, the highest energy electrons in the carbonyl are the lone pairs. So if you bring in an acid, you can actually protonate the carbonyl oxygen first. Then pay attention to what's going to happen here. Then, if water attacks the carbonyl, and we'll have much more to say about this later, this is just a preview. If water were to attack the carbonyl, let's look at what we think about that equilibrium constant. Here's the intermediate that you would get. Do you see now how you're comparing now neutral water as a nucleophile versus a neutral oxygen in the tetrahedral intermediate? Suddenly that looks all kinds more reasonable because you got a neutral water and it's generating the carbonyl oxygen in the tetrahedral intermediate is now neutral. Do you see how that's a little bit more reasonable, a little bit more balanced? There are going to be examples where you need an acid catalyst to make a mechanism happen. And that's usually when you're using a nucleophile that's too weak to get things going. Okay. So with that in mind, those two steps, first nucleophilic attack and then the fate of the tetrahedral intermediate, we're now prepared to consider the two main carbonyl mechanisms of the first several chapters in the text. And those we talked about last time briefly. One is called nucleophilic addition. So nucleophilic addition happens when the nucleophile is strong enough to attack. We'll write that down too. But the leaving group is not good enough to leave. So look at this mechanism. Nucleophile attacks, you get a tetrahedral intermediate. The Y group is H minus, never, never, never going to be a good leaving group. And so there's nothing that can happen to the tetrahedral intermediate. It now becomes the tetrahedral product, and there you are stuck until aqueous workup where the negatively charged oxygen picks up a proton from water, and you end up with this addition product or this 1,2 product. Okay? Second option is when, again, the nucleophile is good enough to attack. And now the Y leaving group is good enough to leave relative to your negatively charged oxygen. So Nucleophile attacks, you get a tetrahedral intermediate. Chloro is a good leaving group. Electrons kicked back down, chloro leaves. Nucleophile is now in place of the chloro group. We call this a substitution reaction because the nucleophile has been substituted in place of the chloro group. We call it an acyl substitution reaction. Acyl refers to this portion of the molecule. An acyl group is a carbonyl group with an R group on one side. And then, of course, the nucleophile refers to the nucleophile. That's obvious. So nucleophilic acyl substitution. These are the two main reactions that carbonyls can participate in, all right? Now, some of you are going to be tempted when you see a nucleophilic acyl substitution reaction to do the following. It's going to seem like it makes sense. It's going to seem simple. The problem is it's wrong, dead wrong 100% of the time. So you are hereby duly warned. Some of you are going to propose a wrong mechanism for nucleophilic acyl substitution. That is, you're going to fall back on 351 stuff and say, why don't I just do the SN2 reaction? The reason that doesn't work is to break the carbon chloride bond, the nucleophile would have to be dumping electrons into the carbon chloride sigma star antibonding orbital. But that's not the lowest energy antibonding orbital in the molecule. The lowest energy antibonding orbital is the pi star. So if you want this to work, what has to happen 100% of the time always is nucleophile attacks the pi star, you get a tetrahedral intermediate, and then you do an elimination reaction. Got it? There's a multiple choice question on your first exam, which I am disclosing to you, which says which of these steps is incorrect, or maybe which of these steps is correct. In any case, some of the incorrect steps are going to show this kind of stuff. Don't let it happen to you. Somebody here is going to let it happen to them, but don't let that be you, okay? All right. So let's now do some sort of specific reactions. And the theme in chapter 13 is going to be reacting really, really strong nucleophiles with carbonyl compounds. So this issue of acid catalysis is not one that we're going to have to deal with in this chapter. We're going to be using nucleophiles that are so strong that they can just attack directly, and we're going to be dealing with the consequences. There's going to be some hydrogen-based nucleophiles, and there's going to be some carbon-based nucleophiles. There's going to be details that you just got to memorize, but for the most part, for mechanisms, they're going to follow the patterns that we've talked about. So before we move on and I start describing these hydrogen and carbon-based nucleophiles, any questions you want to ask? Good, because I didn't want to answer any anyway. So we're all good to go. All right. Hydrogen-based, I actually love answering questions, so please ask. Hydrogen-based nucleophiles. Just as H- is a terrible, horrible, no good leaving group, we generally don't see H- act as a nucleophile by itself. That is, you can buy something called sodium hydride, but it is a salt, and it's not soluble, it's not very soluble in organic solvent. So if you use sodium hydride, you have 0 odds of having H- dissolve in solution, float around, and get to where it needs to be. Instead, for hydrogen-based nucleophiles in organic chemistry, what we basically need is a hydride delivery system. You're too young to have watched Parks and Rec, but there's a scene where Chris Pratt's character, Andy Dwyer, reveals to Ron Swanson the existence of the meat tornado, a burrito that's as big as your head and full of meat. And Ron says, it's like a whole new meat delivery system. It's like, Ron, tacos have existed forever, but what we're talking about here is a hydride delivery system, which is going to deliver the hydride to where it needs to go. Now, it turns out nature uses a hydride delivery system too. It's called NADH and FADH2. We'll deal with that later. Today, we're only going to introduce well, it is on the next page of my notes. Maybe we'll talk about that in a moment. Today we're going to talk first about the hydride delivery systems that we use in the lab. The first is called sodium borohydride. So sodium is just the counter ion. The business end of the molecule is the boron portion, and borohydride is an sp3 hybridized boron that's attached to 4 different things, 4 different hydrogens, and it turns out there's a negative formal charge on the boron. But what you have to understand if you look up electronegativity is that boron is less electronegative than hydrogen. So you could be forgiven for thinking, oh, there's a negative formal charge on the boron, that means the boron's really reactive. But you'd be wrong, because hydrogen's more electronegative than boron. And so in borohydride, all of that negative charge, if you actually calculate where it is, it's out on the hydrogens. So borohydride is a carrier of nucleophilic hydrogens. There's another reagent that's a bit more reactive than borohydride. It's lithium aluminum hydride. This is the more stressed out cousin of sodium borohydride. Aluminum comes 1 row down in the periodic table from boron. It's also, in this case, sp3 hybridized with a negative formal charge on aluminum. But it turns out that the electronegativity difference between aluminum and hydrogen is even greater. So aluminum is even less electronegative than hydrogen and even less electronegative than boron. So lithium aluminum hydride is actually significantly more reactive than lithium aluminum hydride is significantly more reactive than sodium borohydride. As an example, lithium aluminum hydride is so reactive that you have to avoid what we're going to call protic solvents. Protic solvents are solvents that have acidic protons that could be removed, or protons with pKa's that are such that lithium aluminum hydride could remove them. Sodium borohydride, you can use this in protic solvents and it's no problem at all. So it's fine if you think of lithium aluminum hydride as being more reactive and sodium borohydride as being less reactive. Let's give you an example of how these will react. Before we do, it's helpful to just review briefly our ranking of carbonyl compound electrophilicity. Recall that at the top of the list, we have things that either have really good leaving groups or that lack really good electron donors. So at the top of our list for reactivity include aldehydes, ketones. We could also include acid chlorides and anhydrides, things with decent leaving groups. At the top here, I would also include thioesters. We talked about thioesters last time. Things that either have good leaving groups in the place of the Y group, or that have poor electron donors, which is the hydrogen and the ketone. So those are all sort of our most reactive electrophiles. A little bit down the list include esters, which because the oxygen is, the O minus is a poorer leaving group than what we've drawn above, and because the oxygen is a good leaving group, and because the methoxy group is a good electron donor, it's a little bit less reactive. And then sort of least reactive, we're gonna include things like amides, where it's an even worse leaving group, but an even better electron donor than a methoxy group. There are other things in this list, particularly biological types of electrophiles that I'm not including. If you can sort of remember this based on our discussion so far, that's going to help some of what we talk about make a lot of sense. Okay? So let's do some specific reactions. I'm going to pick an electrophile that's at the top of the list. That is, we're going to start with an aldehyde. And we're going to see how that aldehyde reacts with sodium borohydride. So here's a generic aldehyde. Here's sodium borohydride. Here is how borohydride works to deliver hydride to an organic molecule. Remember that most of that negative formal charge on the boron is actually on the hydrogen. So electrons in the boron-hydrogen bond leave with the hydrogen as it directly attacks the carbonyl carbon. This is weird. You've never seen a nucleophile do this before. Most of what you've seen before involved two lone pairs on a nucleophile, then you draw an arrow from the lone pairs to the carbonyl carbon. In this case, you can't do that because H- is a terrible, horrible, no good, very bad nucleophile because it's not soluble in organic solvent. So what happens is boron literally carries the hydride to where it needs to be and then lets it go. All right? So hydride gets delivered to the carbonyl carbon. That breaks the hydrogen-boron bond. That makes a new hydrogen-carbon bond. Here is the hydrogen that was delivered. Here's the tetrahedral intermediate. At this stage, we could ask, relative to the negatively charged oxygen, have we got a good leaving group? No, we got nothing. So we're stuck. We stay there until aqueous workup. That means we add water to the reaction mixture to quench the negative charge on the pink oxygen, and we end up with this as our product. And that aqueous workup step always involves something like this. Okay? So there's our product. Now, it would be silly for you to memorize aldehydes react with sodium borohydrides to give primary alcohols. This is a chant. You can do that if you want. You like singing to yourself, but you don't need to, because if you understand the mechanism, you can predict the product every time, even if you forget, right? But it is true that, yes, with the aldehyde reacting with sodium borohydride, you get a primary alcohol. Let's change it up a little bit, and let's see how lithium aluminum hydride would react with the same aldehyde. It's basically going to be exactly analogous. We're going to have lithium aluminum hydride act as the hydride delivery system. You're going to get the tetrahedral intermediate. Again, you're going to look and see if I got any good leaving groups relative to a negatively charged oxygen. The answer is no, so there you're stuck until aqueous workup, and that will give you your primary alcohol as the product. Okay? Let's keep going. Oh, I will say that your text, I think most of the time, shows the sodium borohydride or lithium aluminum hydride step first, and then they will often include a second step where they literally tell you that they're adding water, and that's fine. I will often leave out the water step. It's just assumed after you do this kind of reaction, there's aqueous workup to add the proton. So if you're doing one of my problem sets and you see, all you see in the problem is starting material and sodium borohydride, It's fine if you just draw this negatively charged intermediate and stop there, but if you look at the key and you see, oh, it's the primary alcohol, what did I forget? You just forgot the aqueous workup step, which is implied, okay? Don't misunderstand, I'm not saying that this reaction happens in water. What I'm saying is, at the end of the reaction, we add water. Okay. Let's do a ketone, shall we? So this time we're going to be a little bit more specific. We'll show the structure of the ketone. This happens to be a methyl ketone, doesn't have to be. We're going to use, let's use just sodium borohydride. And let's not draw the mechanism, let's just predict the product, shall we? So here is the benzene ring. Here is the methyl group. What's my product going to have? Should be an alcohol, okay. And then what? And then a hydrogen. Secondary alcohol. Is that answer correct? Now you're worried, aren't you? Because you think it is, but the fact that I'm asking suggests that you missed something. What? You got to say it's racemic. Why? Oh, I just made a stereocenter at what used to be my carbonyl carbon. My starting material is not chiral. My hydride delivery reagent, sodium borohydride, is not chiral. My product is chiral. If that happens, I have to get a racemic mixture of enantiomers. Now, what you said about from both sides explains where we get that from. I'm just going to draw the other product, and then could you sort of follow up on that and explain what you meant by both sides?
Basically, the starting double carbon bond, because it's sp2 hybridized, it's flat, and so you really don't care which way the hydride comes in. It has the option of either one, and so, but that option does determine the chirality of the product.
Okay, thank you. That's very good. So what you can see based on the pi star that we talked about, remember the pi star is both above and below the plane of the page. There's a node in the plane of the page. That means a nucleophile can attack the pi star from above the plane of the page or below the plane of the page. Those two things have to happen with 50% equal probability because the two faces of this molecule are identical. So you've got to get both enantiomers. Now, fortunately, you got some options for how you want to draw that. You can draw both enantiomers. It's also totally fine to draw one of them, but then, and this is something that chemists do, they'll draw the one enantiomer and then they'll add a plus or minus in parentheses. That harks back to the old days of characterizing organic molecules by optical rotation, which we actually still do. The plus stands for rotation in the positive direction. The minus stands for rotation in the negative direction. The plus minus means you got a mixture of both compounds, a racemic mixture. The other way that you communicate that you get a racemic mixture of enantiomers is you just draw the molecule, but you hedge by not using dashes or wedges. And you got to be smart when doing this because you have to understand when somebody draws a molecule that way, they do not mean that all of those lines are in the plane of the page as though you've just invented a new hybridization of carbon. They assume that you understand, okay, that's tetrahedral, it's sp3 hybridized. One of those should be a dash, one of those should be a wedge, but I'm not saying which because I got both configurations there. Does that make sense? So you're going to see me do that in answer keys on problems, and just got to be smart enough to understand that's what I'm trying to communicate. All of those are fine. Okay, good. Other questions? Yeah.
So with the original molecule, and there's resonance within the phenol ring as well. Does that affect where the hydrogen is at?
So in the original molecule, oops, that's an eraser, not a pointer. It turns out the pi bond between carbon and oxygen is conjugated to the benzene ring. Does that affect where the nucleophile can attack? No, but that's only because of how stable the benzene ring is, and I'm going to punt on that because we're going to talk about it later. Okay, what else? Yeah.
Is it okay in our answers if we write one molecule and then plus an antiverse?
Oh, okay. Right. A fourth way. Good.
Sorry.
Yeah, if you like writing out words, you can you can always do plus enantiomer. And sometimes your textbook will actually do that. So yep, that's fine. Okay. Just as an aside, there are chiral hydride delivery reagents that can favor addition from one side versus the other. And those are very useful. In fact, nature uses them, and I will give you an example of that here. So let's talk about nature's hydride delivery reagent. NADH, which stands for nicotinamide adenine dinucleotide, but I'm going to assume you can look that up, so I'm not going to write it down. NADH is a painfully complicated structure that actually has just one part that's involved in the chemistry, or the actual chemistry that we're interested in. The rest of it is about fitting into the right enzyme active site. So this is the portion of the molecule that's the nicotinamide portion. This is the business end of the molecule. And the hydride that's going to be delivered is one of these two. The rest of the molecule has a ribose ring here. And you're going to learn about all of these pieces in our class this semester. 2 phosphate groups. This is the sort of dinucleotide portion. And then, I struggle with drawing this part. Ooh, are we having fun yet? Here's the other portion. Okay, go ahead and ask. The question that you want to know is, you assume that because I'm drawing it here that I'd like you to have it memorized by yesterday. Is that the question? The answer is no, you don't need to know all of it. You are going to need to know how to use the molecule in a reaction, but fortunately that part is easy. And that's the A part for adenine. We'll learn about nucleotides in another chapter, but this is NADH, and the business end of the molecule is right here. For the most part, we're going to write an R group here attached to this nitrogen for everything else, okay? And we'll have way more to say about NADH. I just want to show you one example so that you can see this, and when we use it in the future, you'll be able to recognize it. We're going to draw now a mechanism of NADH adding a hydride to a ketone in a molecule called pyruvate. Pyruvate is one of the products of a metabolic pathway called glycolysis, and under conditions of what's called anaerobic respiration, where you're working out but not breathing deeply, you can accumulate a lot of pyruvate and your body has to have something to do with it. And so one of the things that you can do is you take, normally NADH delivers hydrides to the electron transport chain where it uses the H- to reduce oxygen to water, and that drives ATP synthesis. But if you're in a situation where you have an excess of pyruvate and an excess of NADH, one of the things that can happen is that NADH will deliver a hydride to the ketone almost exactly like sodium borohydride will. That generates a tetrahedral intermediate that looks like this, only the enzyme that does this is chiral, and so it can choose selectively to deliver the hydride from the top face as we've drawn it here. And then that negatively charged oxygen will pick up a proton from some source, possibly a group in the enzyme active site, but afterwards, the product that you make is this alcohol and only this enantiomer of the alcohol, and this is called L-lactate, or lactic acid. The enzyme that catalyzes this reaction is named actually for the backwards reaction, because enzymes don't actually care which direction a reaction goes. They make it faster both ways. It's called lactate dehydrogenase. But the point is that this enzyme, because it is chiral, is enantioselective. Now, I haven't said anything about the enzyme structure. You would not know which chirality the enzyme should favor. And the way that this works out is simply the enzyme holds onto the molecule and blocks the bottom face so that the hydride can only be delivered from the top face. And it in fact holds the NADH in just the right location so that the hydrogen that's going to be transferred is hovering over the correct face of the molecule. Okay, questions about that? Yeah.
Were you intentional when you were drawing the arrow sizes with one longer, one shorter?
Good question. Was I intentional with arrow sizes, one longer, one shorter? No. Yep. Others?
Were you going to tell us what type of chirality the molecule has?
What chirality the molecule has? It has that stereochemistry. You want to know whether it's R or S?
No. Are you going to tell us, like, since you're telling us that we don't know what size we're going to have? So.
Right. If you're using a reagent that's not chiral, you've got to get both. The enzyme, because it's chiral, can favor one side over the other. That's not something we're going to learn how to predict. Yep. Actually, you just need to see the three-dimensional structure of the enzyme, and you can tell which face it's going to add from, because you can see which side of the molecule the NADH is on. Yeah. But that's probably a topic for biochem. Yeah?
When writing like an answer to a problem, do you expect us to write enantioselective and indicate that, or just leave it?
No, I'm simply saying that a reaction that favors one enantiomer or the other, I'm teaching you a new word, is enantioselective. Yep. What else? Okay, we need to do a little bit more with hydride delivery. We've done so far molecules that were up here that are very reactive and have no good leaving group, the aldehyde or the ketone. Let's just briefly see what would happen if we used an acid chloride. Okay, so let's use an acid chloride, and let's use lithium aluminum hydride. We can draw the mechanism here again. Here's aluminum hydride delivering hydride to the pi star to get a tetrahedral intermediate. Now our Y group is Cl. Is that a good leaving group relative to negatively charged oxygen? Yep, so you know what happens next, which is what? The elimination step, or the kicking offing. The electrons kick down and chloro leaves. Now we got kind of a problem because the product of this reaction, an aldehyde, is same level of reactivity as our starting material. And this is a general problem in organic chemistry. If your product is similar in reactivity to your starting material, your product can start to compete with your starting material for your reagent. So in vocabulary words, perhaps you're okay with this already, but the acid chloride is the so-called starting material. The lithium aluminum hydride is the reagent. The aldehyde here is our product. Now, what would happen from a practical point of view if our aldehyde started to compete with the acid chloride for what little reagent is remaining? You're going to get a mixture of products, right? Because the aldehyde, let's just draw what would happen if the aldehyde successfully competed with the acid chloride for whatever remaining lithium aluminum hydride is present, right? That's just a reaction we've done before, right? A second, or rather a hydride gets delivered to the pi star, you get a tetrahedral intermediate, only now we have no good leaving group, and then after aqueous work up, we get the alcohol. Okay. In practice, when you're in this situation where the product is similar in reactivity to the starting material, there isn't really a good way of stopping here. You could try, you could say, well, let me just add 1 mole of lithium aluminum hydride for every 1 mole of acid chloride. There's a reason that doesn't work. It's kind of interesting, but not enough to talk about. So, but there's another reason why this is a bad idea. Supposing if you added just 1 mole of lithium aluminum hydride, you're going to get a mixture of aldehyde, alcohol, and unreacted starting material. It doesn't work out very well. So in practice, when you've got a good leaving group, we're going to assume you're adding enough lithium aluminum hydride to go all the way to the primary alcohol. That is, with lithium aluminum hydride, you can't stop at the aldehyde. Okay, you just keep going to the final product. That makes sense because the aldehyde is so reactive, we can't stop here. So we add enough of the lithium aluminum hydride reagent to reduce all the way to the alcohol. Yeah?
Is the same true with the sodium borohydride?
Is the same true with sodium borohydride? That's a good question, and the text doesn't show any examples of sodium borohydride being used in this context. So, but there are 2 reagents that I will introduce that are able to stop at the aldehyde. So that's sort of our workaround. Yeah. Other questions? Yes.
I think that the text say like the one caveat with NaBH4 is it can't react with carboxylic acid derivatives.
Right. So we'll talk about that in just a second. There is a limitation to sodium borohydride. A limitation with lithium, and this is maybe a detail you need to memorize. It makes sense though if you understand mechanism. Lithium aluminum hydride can't stop here. Okay, so that's a detail you maybe need to memorize. Before we talk about sodium borohydride and carboxylic acid derivatives, it probably makes the most sense to talk about reagents that can indeed stop at the aldehyde stage. Okay, so to do that, let's again start with. We've started with an acid chloride. An ester is another example of a molecule that's, the ester is less reactive than the acid chloride, but again, if you use lithium aluminum hydride, you can't stop at the aldehyde. What would happen with, you don't have a lot of time to go through the mechanism slowly. What would happen with lithium aluminum hydride is, again, you would deliver hydrogen to the carbonyl carbon. You get a tetrahedral intermediate. Again, you would ask, is there a good leaving group relative to the negatively charged oxygen? Comparing the methoxy leaving group versus the negatively charged oxygen. Again, you would say, yeah, it's reasonable for the negatively charged kicker offer to kick off the negatively charged oxygen. That would get you an aldehyde, but you couldn't stop there. You would need to go on, and I won't draw the mechanism, but your product would also, again, be the primary alcohol. That's true for acid chlorides. That's true for esters. Now, there are two reagents that you can use on acid chlorides / esters that will stop at the aldehyde. Why do we have two of them? Well, synthetic organic chemists like to have options. When you're doing a reaction and your molecule is complicated, there are always all kinds of reasons why your reaction might not work, and if it doesn't, it's nice to have something else to try. So the person who wrote your text is a classically trained synthetic organic chemist, and so Professor Smith, who wrote the text, frequently provides multiple reagents that'll do the same thing. I know that'll drive you crazy a little bit because that's just more stuff to pay attention to, but understand that she's just trying to represent the reality of how organic chemistry is, where having multiple reagents to try gives you some options. The two reagents are these. They're both aluminum based. One of them has kind of an acronym as an abbreviation, DIBAL, which stands for diisobutyl aluminum hydride. This is the isobutyl group, and then this is the hydrogen. Dibal is not negatively charged. Your text doesn't explain this, and so if you looked at Dibal and you're like, how is that a hydride delivery reagent? You're thinking exactly along the right lines. It doesn't look like one. And there's a mechanistic detail that your text doesn't show you for how this works, which I'm going to show you, and then you're going to wish that I didn't, because you're like, more stuff to remember. But if you're curious, it'll provide an answer. The second reagent that can stop at the aldehyde is a slightly less reactive version of lithium aluminum hydride. And the reason it's less reactive is that some of the atoms attached to aluminum are going to be electronegative. So they're going to tone down the reactivity of the hydride. So this reagent is lithium with aluminum hydride. There's a negative formal charge on the aluminum. Then the other three things attached to the aluminum are 3 tert butoxy groups. This one's a real pain to write. Your text will write it like this. Double parentheses, isn't that horrific? Lithium tris tert butoxy aluminum hydride is maybe how you would say that. You're going to call it, when you come to ask me questions about it, you're going to say Dibal and that other one, and I'll know what you're talking about. Okay, so both of these can stop at the aldehyde. So if you take, say, an ester and you use Dibal, that will give you the aldehyde. And if you take the acid chloride and you react it with the other one, the lithium tris tert butoxy aluminum hydride, that will give you the aldehyde. One important point is your text shows mostly Dibal reacting with esters and mostly this one reacting with acid chlorides. It never comes out and says you can only use one with one and one with the other. We're going to just assume that they're interchangeable for our purposes, okay? All right, with that, we've got carbon-based nucleophiles to do next time. So I'll see you on Wednesday when we'll finish up chapter 13.